So composition of compounds. We talked about formulas. We've talked about masses. So the chemical formula, combined with the molar masses of the elements in that formula, gives us relative amounts of elements in a compound. And that's a really useful piece of information. So sometimes we'll use a mass percent composition, or we'll just call it mass percent. So that's how much mass of this one element is there compared to the mass of the entire compound. So the general formula for percent is the part we're interested in divided by the whole thing times 100. And when we multiply by 100%, I put the percent in there because I'm using percent as a unit. The unit is percent, because whatever you're measuring part and whole in, those are going to have the same units, so the units cancel out. So mass percent composition, we're looking at the mass of one element divided by the mass of the whole compound. And then we multiply by 100 to make it a percent. So the percent of X, element X from the formula, is the mass of X in 1 mole of the compound divided by the mass of 1 mole of the compound times 100%. So we can calculate the mass percent from the formula if we know the formula. The mass percent of an element is the same regardless of how much substance you have. So it's an intensive property like density. It doesn't change with the amount of substance. So if you've got a formula, you have to decide how much of this am I going to use in my calculation. The easiest thing is to pick 1 mole, because the mass of 1 mole of the compound is its molar mass. So that just makes the calculations easier. Sometimes we calculate this from experimental data, and we're going to do that in class, in lab. Not today, but another day. Experimental mass analysis. We identify what's the mass of this, and what's the mass of that, what's the mass of the whole compound. We may not know the formula. We can actually use this to determine the formula. So there you have actual data. You take the mass of the element you're talking about, and you divide it by the mass of the compound that you isolated it from, times 100. So it's the part over the whole. If you do that for each element in the compound and add up the percentages, they should add up to 100%, right? Now, when you're doing actual calculations, it might be slightly off. And by slightly off, I mean like 100.3, not 110. It might be a little bit off just because of rounding. So let's do an example. Acetic acid is the active ingredient in vinegar. Calculate the mass percent composition of oxygen in acetic acid. So we want the mass percent composition of oxygen. And notice that this problem has no numbers in it, right? Except for that chemical formula. So the percent of oxygen is going to equal the grams of oxygen divided by the grams of the compound. It's the part over the whole. So the whole thing is the acetic acid. And then we multiply by 100. The unit gram is going to cancel out. Well, they didn't tell us how big the sample was. They didn't tell us how much acetic acid we have. It doesn't matter. The percent oxygen will be the same. But we need an amount for our calculation. So we're just going to choose 1 mole. Choose 1 mole. So can we find the mass in grams of 1 mole of acetic acid? Yeah, we just learned how to do that. Let's do that down here. So we've got 2 times the mass of carbon, because there's 2 moles of carbon in 1 mole of that compound, and 4 times the mass of hydrogen, and 2 oxygens. So 2 times 12.01 plus 4 times 1.008 plus 2 times 16 equals. So 60.052 grams is equal to 1 mole. So I'm going to say, well, that's 4 sig figs. Okay, so that's the mass of 1 mole. So that's what goes in the denominator. Oh, my goodness. So down here, the mass of 1 mole of acetic acid is 60.052 grams. But we want the percent of oxygen, so we need how many grams of oxygen are in this mass of acetic acid? 32. So the numerator, when we show our work like this, is actually hiding in here. So in 1 mole of that compound, there are 2 moles of oxygen, which is 32 grams. Times 100%. The grams cancel. So we have 32 divided by 60.052 times 100. And we're going to end up with, how many sig figs should this have? 4. 2.871%, 53.29%. If you used more precise molar masses, you might come up with a slightly different number, but it should only differ in this last significant figure. So acetic acid is 53.29% oxygen by mass. Any questions? That mass percent can be used as a conversion factor between mass of the element and mass of the compound. Another way to think of percent means per 100, right? Cent is a prefix. There's 100 cents in a dollar, right? 100 years in a century. So when we say that Freon 112 is 69.58% chlorine by mass, 69.58% means 69.58 grams of chlorine per 100 grams of Freon 112. And so this makes a really nice conversion factor. What mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. Well, let's take those numbers and write them down. We've got 58.7 grams of iron, and we're told that this compound is 69.94% iron. So before you do any more thinking about how to do this problem, write the percent as a conversion factor. That means there are 69.94 grams of iron for every 100 grams of the compound, which is Fe2O3. Because if you talk about people and they say, well, 20% of the people out of 100, how many people would that be? 20. 20% means 20 out of 100. 50% means 50 out of 100. So we can take the percentage and make it into a conversion factor. So now we've got our numbers written down. What are we trying to find? What mass of iron 3 oxide? Right? So we're trying to find mass in grams of the iron 3 oxide has this much iron in it. So here I've been given two numbers, and sometimes it's hard to decide which of these do I start with. I know I'm trying to get over here. Well, a percent written this way looks like a conversion factor. This mass of iron cannot be used as a conversion factor. I'm going to start with this, and I'm going to use this as my conversion factor. So I can actually go directly from grams of iron to grams of iron 3 oxide using that percentage. So it's just one step. 58.7 grams of iron. I'm going to do the units first. Grams of Fe2O3 on top and grams of iron on the bottom. In this example, it is important to put the chemical formula there because this is grams of one thing and this is grams of something else. And so we need to specify grams of what? Grams of iron, cancel grams of iron, giving me grams of the compound. Now I look at this percentage as I wrote it out here, and 69.94 grams of iron. Well, I put grams of iron on the bottom. I don't need to rationalize or try to remember or anything. I just follow the pattern. So I'm going to put the number with its unit. And in the numerator, I'm going to have 100 grams. Just a note about sig figs. When we're expressing this percentage as that number per 100, that means per exactly 100 grams. The sig figs are in this number. The 100 is exact. There are other ways to do problems like this, and if you're good with percentages, go for it. I'm talking to the people that have a hard time with them. This is a good pattern way of doing it. So my numbers here, I've got 3 sig figs in the 58.7, so my answer should have 3 sig figs. I'm going to underline that number, that digit, and write down 2 more. And then I've got grams, and then when I round this, it's going to be 83.9 grams of the iron oxide. And then you should always ask yourself, does that answer make sense? If there's 58.7 grams of iron, should the mass of the compound be more or less than the mass of the iron? It has to be more, right? And this answer is more. If you get your percentage in upside down, you'll end up with a number that's smaller. And that's like saying, out of 100 people, 150 of them have green hair. Well, there aren't 150 people in the 100, right? It's not possible. Questions? I don't know where the green hair came from. Make stuff up as I go along.